Using the parallel and series rules that we've learned about capacitors and resistors can simplify a lot of circuits, and that's called circuit simplification, but it won't fix everything. In the circuit below, for example, we have 2 batteries and 3 resistors, and because of the positioning, the batteries aren't in series or parallel with each other, and the resistors are not in series or parallel with each other. The tops of the resistors are connected, but the bottoms aren't. So we have to learn something new, and these are called Kirchhoff's rules or sometimes Kirchhoff's laws. They're kind of simple, but one of the things that causes people to stumble in the beginning is it seems like you have an awful lot of freedom, so much so that maybe you can't expect anything useful to come out of it, but we'll see why that's not the case. The first one we're going to look at is called Kirchhoff's loop rule or Kirchhoff's voltage law. This says if we move around a circuit and return to our starting point, the sum of the jumps and drops in voltage must be 0. This is really just connected to the conservation of energy, and we can compare it to the situation last semester where we had a roller coaster. If we assume there's no friction and there's no external input of energy like a chain drive, the total change in both potential and kinetic energy is 0 from one ride to the next. In the picture from your book explains this. It says if you go through a resistor in the direction the current is traveling, if you cross the resistor that way, you drop in potential by an amount IR. On the other hand, if you go against the direction of travel of the current through the resistor, you increase the potential by IR. If you go across a battery from the minus terminal to the plus terminal, that gives you a jump in potential equal to the battery's voltage. If you go the other way, it gives you a drop in potential equal to the battery's voltage. We just have to memorize these, but they're not really that hard because you can imagine you're on a closed track, a closed loop track in the woods. If you're walking beside a stream and you're going in the direction the current's going, you must be moving downhill to a lower potential. If you're walking opposite to the direction of the current, so you're walking upstream, you must be moving uphill. That's all that we're really saying with these figures A and B. On the other hand, if there are stairs, if you're climbing up the stairs, you're increasing your height, and if you climb down them, you're decreasing your height. Now that we know this, we can go back and try and solve our earlier problem. We got 3 separate branches here, so we can expect to need to find 3 separate currents. Here I've put in names for the currents, I1, I2, and I3, and these directions. Where did I get the directions from? Completely random guess. You can make all of them up, all of them down, 2 up and 1 down, 2 down and 1 up. It doesn't matter. Look at this example from last semester to see why. We've got a block on an inclined plane attached by a rope over a pulley to another block hanging off the inclined plane. Which way is this going to move? Well, we have no idea. We don't have any of the numbers, and unless you're really good at doing this in your head, you'd have to work it out anyway. This block could go up the plane or down the plane. You just pick a direction and say, all right, I'm going to assume acceleration is positive. When you get to the end, after you've done the whole problem, if you get a negative number, that just means, no, it accelerates in the other direction. The same thing will happen here. When we're done, if we get a negative number for I1, for example, it will mean current's really flowing down in this branch. Now we have to decide what loops we're going to use and what direction to go around. Again, this won't really matter. I'm going to pick the left side of the circuit and go clockwise. So this is the left half. I'm going to go clockwise starting from the bottom. I can go either direction I want, counterclockwise or clockwise, and I can start from any point along here. All of that leads to the same result, believe it or not. So if I do that, then I apply these rules. I go across the battery. I pick up plus V1 or plus 9 volts. I cross this resistor in the direction the current is going, so that's minus I1R1 or minus 3000 ohms I1. Here I'm going upstream of the current, so I get plus I2R2 or plus 750 ohms times I2. Then I'm back to my starting point and I'm done, and the sum of all that has to equal 0. So the equation is this: 9 volts minus 3000 ohms times I1 plus 750 ohms times I2 equals 0. That's one of our equations. We know we're going to need 3 since we're trying to find 3 variables. Now my next choice is going to be right half of the circuit. I'm going to go counterclockwise this time. Why not? And I'm going to start here at the bottom. Again, I could start anywhere. It doesn't matter. When I go across this battery, I pick up plus 12 volts. I'm going upstream of this resistor, so I'm going to pick up I3R3, or plus 1,000 ohms times I3. And then here, again, same direction across R2, I'm going to pick up I2R2, or plus 750 I2. Go back to where I start. That all has to equal 0. So here's my second equation. 12 volts plus 1,000 ohms times I3 plus 750 ohms times I2 equals 0. We need one more equation, and you might think to yourself, what about the outside path around the circuit? Again, either direction, whatever starting point I want, but I just ignore the middle branch. That would give me a third equation. Will that work? It turns out it won't, and if you've had linear algebra, the reason it won't is it's not linearly independent. Now, if you haven't had that, here's the reason. We need as many equations as variables. You know that there's no single solution to 3x plus 5y equals 10. There's an infinite number of solutions to that. If I want to pick one out, I need one more equation. Okay, how about if I give you 6x plus 10y equals 20 and say, okay, there's your second equation, now solve it. This won't work because this is just a constant 2 times the first equation. It doesn't give you any new information about how x and y are related. So if I take the outside loop, I'm not learning anything that I don't already know from the two inside loops. If I want, I can take the outside loop and one of the others, but taking all three of them doesn't give me any new information, so we can't do that. Now we need the next of Kirchhoff's laws, and this is sometimes called the current law, sometimes called the node rule. So a node is a place where two or more wires meet. What we really need is a place where three or more wires meet, and that's called an essential node. The reason this matters is two wires meet anywhere. I can point to any part of this circuit and say, okay, I've got a wire coming in from this side and a wire coming in from that side, even though I don't have any break in the wire or anything. So it's kind of a pointless idea. The essential node, on the other hand, that's where we have three wires coming together, and that's what a normal person would call a node. Now, the rule says the sum of the currents entering a node is 0, or we could say it says the sum of the currents leaving a node is 0, or we could say it says the sum of the currents entering equals the sum of the currents leaving. This all goes back to the conservation of charge. However many electrons go into a point must go out of it, or we're going to get a charge buildup like a capacitor that will eventually match the driving voltage and will stop it. We have two essential nodes here, top center and bottom center, and it doesn't matter which we pick. I'm going to pick the top. We have incoming currents from I1 and I2 and outgoing currents from I3. Remember, this is because I've made up the directions as up for I1 and I2 and down for I3. So I can write this as I1 plus I2 equals I3. Now we can solve our equations. If you're doing this on a computer, you can plug them in and have it spit out the solution very quickly. And a lot of you have calculators that will do that. But anyway, if we're not doing it that way, notice that we could use any of the three versions of the KCL. They'll be equivalent. The sum of the currents in would be I1 plus I2 minus I3, since a current out is a negative current in. The sum of the currents out would look like negative I1 minus I2 plus I3 equals 0. We could easily prove they're all the same with some simple algebra. Now, while we're at it, what would our other equations look like if we had chosen to go in the opposite direction? We'd be multiplying everything by negative 1, which doesn't change our equation, because 0 times negative 1 is still 0. Wherever we start, we get the same pieces in our equation, so it doesn't matter where we start on our loop. That's where all our freedom comes from. Now, if I give this to you on a test, which is pretty likely, I don't want to pick through 30 different versions of the problem, so I'll probably give you a picture more like the one above, where I've chosen the names and the directions of the current. You still get to pick the starting point and the direction that you move around the loop, but I've chosen that stuff to make my life easier. So, if we aren't using the fancy calculator, we can solve this by elimination. We have these three equations, our two loop rules, and our current rule. We can use the third equation to get rid of I3. here, since we know it's equal to I1 plus I2. So we can rewrite it like this. Now, if we look at the first equation and this equation, we see that they both have a voltage and I1 and I2 in it. If I multiply this second equation by 3, I'll get 3,000 ohms I1. I can add these two equations then. The I1 will cancel. So 3 times this equation plus this one gives me 45 volts. The I1 term cancels. Then I get 6,000 ohms times I2. This is a very fast one to solve, obviously, and I get I2 is negative 0.0075 amps. Since it's negative, that tells me the center current was really moving down. I guessed wrong on that one, but no big deal. I can now put this I2 back in the first equation and solve for I1, and I get 0.001125 amps. This is positive, so I guessed right here. It is going up. Now the last current we could solve a bunch of ways. We could put in the value that we know for I2 into this thing and solve for I3. It's easier to use this one though. I1 plus I2 equals I3. When we do that, we get I3 is negative 0.006375 amps. So this direction was also wrong. Doesn't matter though, we've got the right answers. Now, if I do put this problem on a test, which again is kind of likely, the biggest part of it is finding these 3 equations, getting them right, because this is where the physics is. Getting the answer from this is important, but it's not as important as these equations, because that's just the math part. And again, you know, a relatively cheap calculator will do that for you. Now, there's another way to do this, and I'm only telling you this because to me it's so much simpler that I feel guilty hiding it from you. There are a lot of techniques for solving circuit problems, and if you take a junior level circuits class, you'll learn them. This technique is one that you typically only see there, but it's so much easier as far as I'm concerned. I want to go ahead and tell you about it. You do not have to use it at any point, and you can, fast forward if you don't want to see it. Now, if you choose to use it to solve a test problem, I still want you to put these 3 equations in. I still want you to find those because, again, that's the important part at this level. This new way is called the node voltage method, and the idea here is our 2 essential nodes, we pick one of them as ground and find the voltage at the other node. Since there's only 2, we only need to find one voltage rather than a bunch of them. This means this is going to be a single equation instead of 3. If the bottom node is ground and we call the top node, call its voltage V, what we're essentially going to use is the Kirchhoff current law and say that the sum of the currents leaving the top node must be 0. Now, the current can leave the top node through 3 different paths. What's the current on each path? The current leaving on the left side, remember, here's our picture again, way back up here. The current leaving this way is going to be the delta V across this resistor divided by that resistance. So the delta V is this V here minus 9 volts divided by 3,000 ohms. So that's pretty quick. We get that part of the equation. So V minus 9 volts over 3,000 ohms, that's the current leaving that node. Now, on that path, notice that it's V minus 9 and not 9 minus V because we're doing current leaving and not current entering. For the middle path, it's even simpler. It's just a single resistor that connects the top and ground nodes. So top node minus ground is V minus 0, or just V, over 750 ohms. And finally, I3, again, we do V minus 12 volts because that's the voltage difference across the 1,000 ohm resistor. We write I1 plus I2 plus I3 like this. And now we have one equation, one unknown. We can find a common denominator by multiplying by 3,000. And what we get out of this is our voltage at that top essential node is 5.625 volts. Once you know that, everything else is easy. On the left path, the battery is 9 volts, the top node is 5.625. I know current is going up because it's larger potential at the bottom. And I do the math. Delta V over R is my current. This has to go up. The middle one has to go down because V is 5.625 and the bottom is 0. The size of the current is delta V over R, 0.0075 amps. Now this is downward. Notice that I defined I2 as upward, so keep in mind we got a negative last time. That's the reason if you go back in the video and look at what I got for I2 the other way, there was a negative. Finally, on the right side, top is 5.625, the battery is 12. Again, this one is negative. We've got current that's really going up. The current leaving is negative, which means it's flowing into the upward node. This, in my opinion, is much easier than doing the elimination, solving it the other way. But again, I want to see the equations that you get from KCL and KVL, even if you do use this to solve it. Now, the last thing in this chapter is charging and discharging a capacitor through a resistor, and this is called an RC circuit. This is a more realistic situation than we've had so far because in any real circuit there will always be at least some resistance, even if it's the battery's internal resistance. So here we have a battery, a resistor, a capacitor, and a switch. If we're in the A position, the capacitor is charged by the battery, but the current is reduced by the presence of the resistor. We can, and that's what it would look like here in the middle. We can use Kirchhoff's laws to figure out what the charging current is by looking at this middle figure. We go around this clockwise, we get the expected E for the EMF, we get minus IR for the battery, and the potential difference across the capacitor is Q over C. So E minus IR minus Q over C equals 0. This doesn't look like a hard equation until you realize that I is really dQ dt, and this thing is really a differential equation. Now, you're not supposed to know how to solve differential equations in this course, but you can verify the solution because that just requires regular calculus. This is the solution, C times the battery voltage, and then multiplied by 1 minus e to the negative t over RC. This exponent, t over RC, this has to be unitless so that we know that RC must have units of seconds. This is called the capacitive time constant, tau c. We don't really need the c right now since it's our only time constant, but eventually we'll have another one. You can verify this is a solution of the differential equation by just plugging it in. Put the dq dt in there, do that math, and see that it works. If you plot it as a function of time, you'll see that it looks like this. This means the charge asymptotically approaches C times the battery voltage. If we wait one time constant, we'll be at about 63% of the way charged. If we wait 5 time constants, we're at 99% of the maximum charge, and this is usually enough for us to consider it fully charged. If you really want to be sure, wait 10 time constants, and we get much, much closer to our final value. Now, while this math is in general too complicated for most people to do in their heads, remembering this 5 or 10 time constant thing makes the math much simpler. For example, let's say we have a 1 microfarad capacitor and a 100 ohm resistor. Our time constant there is 0.1 milliseconds, so if I just remember this 5 times the time constant rule, I know it'll be 99% charged in half a millisecond. Now we could find the voltage across the capacitor at any time with this same formula because Q equals CV, and I could just divide by C. If we do that, this should be a V here rather than a C. This should be the battery's voltage rather than C. And other than that, it's the same formula. Now, finding the current at time t means we take the derivative of the Q as a function of time formula. When we do that, dQ dt, it looks like this. Notice that the C cancels out top and bottom. We get battery voltage over R. That's what we would call current, right? That would be our expected current. And it drops off exponentially with time. There's a reason that we expect the current to drop exponentially. When we connect an uncharged capacitor to a battery, the charges see this wide open empty space, and they're able to get out and get away from each other and get some room. That looks good, so many charges move in a hurry, but as they accumulate on the capacitor, it starts to look less and less worth the trip to the charges that are still in the battery. Physically, this is because the charge increases on the capacitor, so the voltage increases on the capacitor, and that means the difference between the battery voltage and the capacitor voltage is dropping, and that difference is what drives the current through R. In the third picture here, we have lost the battery, we've taken it out of the system, and we're just discharging the capacitor. This is going to look very similar to what we had before. Kirchhoff's law, now we get this. Still a differential equation, but it's a little simpler. This time Q as a function of time looks like this, and you can see that it's dropping exponentially. The current is going to look almost the same except for the negative sign, and it's the same reason. Very large current initially, which is just voltage across the capacitor divided by resistance of the resistor. VC is the same as the voltage across the resistor in this circuit, and as the capacitor discharges, this voltage drops, the current drops with it. Now, a very common lab for this second semester physics course is to measure the discharge of a capacitor as a function of time to see if it matches what we've set up here. Now, we don't have an easy way to measure the charge on the capacitor directly, but if we use Q equals CV, we can measure the voltage and find the charge. When you do this lab, unless you're really careless, you'll get data that matches the theory better than any other intro lab you've done. When you have Excel plot your data and fit an exponential curve to it, that R squared value will be probably about 0.99.